So now I will explain you about the feedlot problem number 7 that you did at the class assignment. So here's the problem, and then let me just go to the answer. So let me go to the variables first. So I use X as numbers of 100-pound sacks of pellets, and Y is number of 100-pound sacks of corn. Okay, so from this table I can see that per 100 pounds of pellets contains 25 pounds of protein. So 100 pounds of corn contains 10 pounds of protein. So from the perspective of protein, 25x plus 10y, 25x plus 10y, at least, it means it is greater than and equals to 250. Okay, so from mineral point of view, 12x plus 10y must be greater and equals to 200. And then 20x plus 32y must be greater and equals to 512. So we have all of this translated. And don't forget that we need to simplify the equations that we have, of course. So I divide like this one, I divide all by 5, I divide all by 2, I divide all by 4, I divide all by 12. And for this one, the total food no more than. It means that I cannot have more than 3,000 pounds per day total pellets and corn. Since one sack of pellets contains 100, so we're speaking about and this one is 3,000 pounds, so we have to divide it by 100 so to know how many sacks total that we can have, no more. So this is the translation. So the total sacks of pellets plus the total sacks of corn must be less than equals to 30, since 30 is speaking about not the pounds, 30 sacks. So but this one is 3,000 pounds. Since 30 sacks contains 3,000 pounds, so this is a correct statement. Can you get it? So yeah, keep in mind that the X and Y are speaking about the sacks. So before I go further to the graph, I need to make sure whether my equation or inequality here is good enough for me to graph it directly. So for this one, I think it's good enough, since I can use the x-intercept and y-intercept method. But this one is not good enough, since 100 is not divisible by 6. It means I need to convert into slope-intercept form, and yeah, this one is better. I can graph this directly, right? So the next one, like this one also, is not good enough for me to graph it directly, so I change it into the slope-intercept form, and this one is good, since I know that the y-intercept is 16 and the slope is this one, so I can graph it directly. And when I simplify this, I think it's good enough, since I can use the x-intercept and y-intercept method, and this one is good enough. So let's go graph. To graph the first one is we are using the x-intercept and y-intercept. The x-intercept equals 10 and the y-intercept equals 25. So 25 and 10. Okay, this red line is the graph of this one. But still we need to shade it so it is greater than equals to, and the y coefficient is positive, so it is above, right? And then let's go to this one. This one, the y-intercept is 20 and the slope is negative 6 over 5. So it begins with 20, this is 20, and then negative 6 over 5, down 6 times, 1, 2, 3, 4, 5, 6, and run 5 times, 1, 2, 3, 4, 5, done. And then just graph it, right? So the next one is this one. So the y-intercept is 16 and the slope is negative 5 over 8. 16 here, and then count 5 times to below, 1, 2, 3, 4, 5, and then 8 times go to right, 1, 2, 3, 4, 5, 6, 7, 8. So this one. So you just graph it. Okay, so let's just sheet the second one. It's greater than equals to. It means the second one also is going to the, okay, and then the green one also to the above, and then this one. Okay, how to graph this? Of course, since my axis doesn't contain 40, it means I have problems here. I cannot use the x-intercept 40. The y-intercept is good enough, it's 10. So I begin with 10 here. Okay, but how do I find the second pair without involving 40, since my x-axis is not cannot contain until 40? So I use the table of pair here. Right, the first one is when y equals 0, when x equals 0, y equals 10. And then I will use when x equals 10 or 20. When x equals 20, y equals 5. Right? 20 plus 20, 40. So how to graph this one? You can be flexible. So the first pair is 0, 10 here. And the second one is 20,5. 20,5 here. So 0, 10, and then just connect that. You can have this line. And then to fulfill or satisfy the inequality, greater than equals to, so you sheet it to the above. Okay, and then the last one is x plus y equals 30 for the line. 30, x-intercept, y-intercept, 30, 30, right? I mean, this is the y-intercept, this is the x-intercept. So, and then just draw the line, and then since it is lesser and equals to, you need to sheet below. So in the end, I have the feasible region. Let me show it now. Yeah, this is it. This is the feasible region. Well, I see it green. Actually, it shows you all the pairs inside of the feasible region that will satisfy all of these restrictions. But I put the dots here in order that I open the possibility that if we accept only integers as your answer, it means we can have, but this is a lot. I don't want to count how many pairs we have here. But there's a lot of pairs here that is acceptable since it satisfies all the restrictions. But from all of these pairs, we try to find which one is the optimum one. But for this perspective, the optimum, since this is the cost, we need to minimize the cost, right? Something we have to spend, we have to minimize. So the optimum pair will be the minimum one. Let's find which of this pair will give us the least possible cost that we have to spend. So so from the textbook, it is explained that the one sack of pellet will cost you $16, and one sack of corn will cost you $8. So the total dollars that you have to spend is 16x plus 8y. So let's just use the testing line, and I will use the assumption if the dollar is 160, since I want to divide both by 16. Okay, I use 160. So with that, the x-intercept will be 10, 0, and the y-intercept will be 0, 20. So let's graph this testing line. So this is the testing line. Well, actually it's outside the feasible region, but it's okay. So since this is outside the region, so we have to slide it right, of course, not left. And if you want to find the minimum, it is the first pair it touch. If you want to find the maximum, it is the last pair it touch. Right? So yeah, let's just find first which pair will give us the maximum cost. That is not the objective but let's just by sliding it. Well, yeah, if we are looking for integers pair, it means this one is the maximum, is the pair that is acceptable to give the maximum cost, which is this one is 27 sacks of pellets, and 4 4 sacks of corn. But if you accept non-integers as your answer to find the maximum, let's just slide it, and in the end you will find that the last pair is this intersection. This intersection. Okay, these intersections is the one that will give you the maximum cost. Interesting, right? The maximum cost. And you can be certain, you can compare with the other pairs here, you can be certain that this one, the non-integers pair, will give you the maximum one. So let me just slide it again, just to make sure. Do we really yeah, it's clear. The last one is this one. But again, if we are only accepting integers, it means this one is the pair. If we accept non-integers, this is the pair. Okay, sorry for revision. Actually, this pair is 26,4, not 27, right? It's 26,4. But yeah, that's if we are finding the maximum. But that's not the case, right? We want to find the optimum one, which is the minimum, the least possible cost. Since we are, of course, in spending money, we want to make it lesser and lesser, right? So let's continue answering first the questions here. For B, is it feasible to fit only corn? So if we fit only corn, it means there is no pallets, no sacks of pallets. So the x equals 0. Is it feasible? So do we have inside the feasible region a pair where the x equals 0? The pallets 0. The x equals 0, yes, we have. This one are all the pairs that is 0,25, 0,26, 0,20. So it is feasible to fit only corn, since if we choose this pair, is inside the feasible region, we fit only 0 pallets, but 26 corns, 26 sacks of corn, right? So it is feasible. It is feasible. But how about only pallets? Only pallets means there is no corn, no y, the y equals 0. Do we have inside the feasible region a pair, any pairs, that its y equals 0? No. Since the least value of the y, if we are looking for integers, it is 4, right? So inside the feasible region, we can only accept 4 as the least value for sacks of corn. Or if we are looking for in non-integers, well, you have to find the value of this intersection. So the answer for the second question is no, only pallets. Okay, this one we have already done it, the D. So yeah, this one actually help you how if you substitute the D into 240 and so on. So if we assume that it is $160 the cost, so this is $160. So actually there is no pair inside the feasible region that give you $160 for the cost, since this line shows all the pair that will give you $160. So yeah, so all these pairs inside the feasible region will give you more than $160 for the cost, right? So yeah, let me skip this one. Actually, you need to graph two testing line here, 240 and 200, and then show that there are 4 minimum optimum points with integers. So let's now find the minimum one. So let's slide this one carefully. Okay, since we are finding the integers, okay, let me just slide it carefully. Now, if we want to find non-integers intersection, a non-integers pair that give you the least possible cost, it is here. This one. This intersection. Okay, that intersections is the first pair that this testing line touch. When I slide it carefully, that is the first pair. So if we accept non-integers, this is our answer. And you have to find the intersection between the orange line and this black line. So this line and this line, find the intersection, and that intersection will give you the optimum point. But since we are expecting integers here, okay, integers, so let's continue. Let's continue to slide it and find which integers pair it touch first. See? Okay, let me just this one, this one, this one, and this one. So yeah, let me just color it there. Okay, so yeah, this one, this one, this one. That one. So yeah, these four pair. So let me just write down all these four pairs, and then let's see, is it right that these four pairs will give you the same cost, the same value of D, and which is the least possible value of D that is brought by the pairs of integers. So here it is, the four integers that we find by the testing line as the first four, the first pairs that the testing line touch, which is 2,20, 3,18, 4,16, and 5,14, which is, it means 2 sacks of pellets, 20 sacks of corn, and etc. So actually this combination will give the same exactly $192 for the cost, which is this one is the least possible cost from the pairs of integers in this visible region. So you can be certain if you use other pairs than this one, any pairs of integers like this one, or this one, or this one, or at least, or this one, it will give you more than $192. Since the objective is to find the minimum or the least possible cost that we want to spend, it means we can choose this combination or this or this or this to be to be our answer, since all of this will give you the same cost, which is the minimum value. So to answer the other questions, you can refer to the image that I share about the complete answer for these problems. But I just want you to notice that to answer G, find the exact point of intersection of the two boundary lines that meet the actual non-integers optimum point, it means we are referring to this one. Okay, this one. Okay, since when you slide the testing line, this actually the first pair that it touch, if we consider the non-integers as the answer. So how much could Mr. Earth save per day? So actually we just find the difference between using the non-integers pair with if we are using the integers pair. So what is the difference of the cost? Okay, so yeah, that's it, how you answer this kind of linear programming.